Hello, welcome back to the second course in physics. And in this lecture, we will still be discussing topics related to electric current and resistance. In this lecture, we'll be concerned with calculating the resistance of conducting objects. We will encounter the different ways of looking at the resistance and calculating it. So we will encounter the problem of a non-uniform conductor, non-uniform in shape, geometrically non-uniform, because it's simple to calculate the resistance of a uniform conductor. We will also, as an example, consider the problem of two concentric cylindrical conductors, two concentric cylinders, and we will calculate the resistance of this system. We will next consider the problem of connecting resistors in series and calculating the equivalent resistance, which is a topic that is important in the case of analyzing electrical circuits. We will also consider connecting the set of resistors in parallel, and we will be concerned with evaluating the equivalent resistance for such a set of parallel resistors. And then finally, we will discuss the effect of Joule heating as the current passes through a conducting wire. These will be the topics of this lecture. Previously, in the previous lecture, we have defined the resistance and the different parameters that the resistance depend on. And we have shown that the resistance of a conducting object depends on the material of which the object consists of through the resistivity rho or the conductivity sigma, and the parameters that depends on the number density, the mean free time between scattering centers, and so on. And also it depends, in addition to the material itself, on the geometry of the current carrier. And we have defined the resistance previously, and in this lecture we will be applying this definition to calculate the resistance of different objects in some special cases. So in the beginning, let's assume that the current in the conductor spreads out uniformly over any point in a cross section of the conductor, and we neglect fringing and edge effects. So that means in each little element of the cross-sectional area, the current density is the same, uniform. And in this case, the resistance in the most general form is given by the resistance of a small element of length dx of the conductor is given by rho times dx, the length of that conductor, divided by the cross-sectional area of that conductor carrying the current. And that is the rho over s dx is the element of resistance, which is associated with the element of the conductor of length dx. And if we are interested in calculating the resistance of the whole conductor, all of it, so we have to integrate over the length of the conductor from 0 to L, considering that L is the length of the conductor. So this gives us a relation for calculating the resistance. R is equal to the integral from 0 to L of rho over S times dx. And this formula, we can apply it to evaluate the resistance of a conductor in some cases where the geometry is simple to deal with, and where we can find a simple function that can be evaluated simply by this integral. And here we will encounter some problems that illustrate this method of calculating the resistance of a conductor. And the first case, we consider that we have a non-uniform conductor, non-uniform in the sense that it is not uniform in shape. So we take, for example, this shape of the conductor, non-uniform conductor, where its cross-sectional area from one side is different than the cross-sectional area from the second end of it. And we assume that the radius of the cross-sectional area on one end of it is A, and the radius of the cross-sectional area on the other end of it is B. And the length of the conductor, we consider it is L, and we consider that the resistivity of the material of which this conductor is made of is rho. Then we pass current through this conductor, and we are interested in calculating the resistance to the flow of current actually, to the actual flow of current, as this figure shows, where the current is flowing parallel to the axis of this shape. And if we recall the previous definition, R is equal to the integral from the beginning to the end of the conductor of rho over S dx, we notice that here in this particular case, S is a function of X. As we go from the first end to the second end, the cross-sectional area S changes. So it's like a function of X. So in order to perform the integral, we have to determine the cross-sectional area at each position along the length of the conductor. And doing so, we notice that S of X is simply equals to pi times the cross-sectional area at any position X, and this is simply A times A plus B minus A over L times X. So this the first term A is coming from the radius of the first cross-sectional area. The second term is coming from the slope that reaches a different radius. So this would be the A plus B minus A over L into X times X. This would be the radius of a cross-sectional area at a position X from the first cross-section. So this radius squared times pi gives the cross-sectional area at any position X from the from the smaller cross-sectional area. So this formula gives us S as a function of X. And now we have done that, then we can perform the integral, the previous integral. R is equal to rho dx over s, and we substitute for s of x as a function of x. Then R is equal to rho over pi times the integral from 0 to L over the length of the conductor dx over a plus b minus a over L times x all square. This is simply rho dx over s, but s is stated as a function of x, and we integrate over x from 0 to L. And this integral is simple, and the result is R is equal to rho over pi times L over b minus a times square brackets minus 1 over a plus b minus a over L times x, and that is evaluated from 0 to L. And this gives the result R is equal to rho over pi times L over b minus a times, in parentheses, 1 over a minus 1 over b. And we can simplify this formula by considering the magnitude in the second parenthesis as being b minus a over ab, and b minus a in the numerator and denominator, they cancel out, and we are left with the result R is equal to rho times the length of the conductor divided by pi times AB. This is the resultant, the resistance resulting from this calculation using the integral form. And we can have a check. We can check this formula because we know what is the resistance of a uniform conductor, a uniform cylindrical conductor. It is simply rho times the length over the cross-sectional area, which is pi a square or pi b square. So take the limiting case where a and b are equal. If we put a is equal to b, then we will have R is equal to rho L over pi a square, which is simply the resistivity times the length over the cross-sectional area of the cylindrical conductor. In the case of A equals to B, we will have a cylindrical conductor. So this checks out this formula. And this is the first example for calculating the resistance by using the definition of the resistance. And now we take another example, which is two concentric cylinders. If we have the case of one cylinder concentric with another cylindrical shell with some material in between, and the material between the two concentric cylinders has resistivity rho. This is the conductor that we are interested in calculating the resistance for it. But now, if we have this geometry of two concentric cylinders, the resistance depends on how is the current flowing. For example, if the current is flowing axially, then the cross-sectional area is something. And if the current is flowing radially, if it's going from the center, going radially towards the outer shell, then the cross-sectional area and the geometry of the field lines are different, and it gives a different answer. So this is what we are interested in, and we will consider both cases. And first of all, for the case of the two concentric cylinders, we we have this first cylinder is of radius A, and the second cylinder, the outer cylinder, is of radius B, and the material in between has resistivity rho, and we take part of this system, the part of this system which has a length h, and we calculate the resistance of that part, which is of length h. Of course, the length that we select is arbitrary. It's not of any significance. Now, if the current is flowing axially, parallel to the axis of the cylinders, then we notice that the cross-sectional area is exactly the same as the current flows along the cylinders parallel to the axis. The cross-sectional area is always equal to the cross-sectional area of the outer shell minus the cross-sectional area of the inner shell, because the current is flowing between the two shells, between the two cylinders. So the total cross-sectional area where the current is flowing is simply pi b square minus pi a square. That is the area where the current flows. And this area where the current flows between the two cylinders is constant all through. So rho is constant, the cross-sectional area is constant, so that means dx, when integrated, it gives simply the length of the conductor. And this, we get r is equal to rho times the length of the conductor, which is assumed h, divided by the cross-sectional area pi times b square minus a square. So this is the resistance of two concentric cylinders if the current is flowing between the two cylinders and axially parallel to the axis. Considering that rho is, again, the resistivity of the material between the two cylinders and not necessarily the resistivity of the material of the cylinder itself, unless current is flowing there, of course. That is the resistivity of the material where the current is flowing. So we have to keep that in mind. And now we have a more interesting and maybe complicated case where the current is flowing radially. So if the current is flowing radially, following the radius, the radial direction, from the center from the axis towards from one surface of the inner cylinder to the surface of the outer cylinder, and the current is flowing radially from the axis going out towards the outer shell. In this case, the cross-sectional area that the current crosses at a certain point as it goes in its path from the inner cylinder towards the outer cylinder, the cross-sectional area is simply 2 pi r times h. It is the lateral area of the cylinder, rho over 2 pi r h. Of course, this cross-sectional area depends on where we are between the two cylindrical surfaces. It is proportional to the radius of the cross-sectional area which the current crosses. So that means we have found S, the cross-sectional area, as a function of the path where the current flows. And this is the desired relation or the required relation for the calculation to be accessible. So in that case, we substitute these values in the integral, and we reach the result r is equal to the integral from A to B. That's where the current is flowing from the surface of A to the surface of B radially. Rho times dx is the path. In this case, it is dr because the current is flowing radially, divided by s, which is 2 pi r h. So this is a simple integral to perform again. And notice that rho is constant, 2 pi is constant, and h is constant. They can be taken out of the integral, rho over 2 pi h. And then we are left with integral from A to B of dr over r. This integral gives len r. When evaluated from A to B, len r, it gives len b minus len A, or len b over A, len the quantity b over A. So for radial flow of current between the two concentric cylinders, for a radial flow, the resistance is simply the resistivity of the material across which the current flows divided by 2 pi h, and h is the length of the conductor, times len b over A. This is an interesting result, and it has the right dimensionality, of course. It has the right dimensionality as expected from the definition of the resistance. We have to mention here that generally the resistance is calculated from the relation between the voltage difference across the conductor and the current flowing in that conductor. That is the most general procedure for calculating the resistance of a conductor, because sometimes the geometry of the conductor is very difficult to deal with, and performing the integral that we have done in the previous two examples could be difficult to be handled. And in addition, maybe the material itself of the conductor is not known, so maybe we don't know the resistivity or the conductivity of the material of the conductor in order to evaluate its resistance following the previous procedure. So the safest way is to bring the conductor, apply a voltage difference across the 2 points, and if the conductor is ohmic, as we have discussed before, then the relation between the voltage and the current flow across the conductor would give us the resistance. This is a very convenient and quick way, done by measurement rather than by calculation. So that way we have two methods of calculating the resistance. And now we come, once we have defined the resistance, we deal with resistors as just objects with a given resistance. And now, for the purpose of the electrical circuits, we need sometimes to connect resistors in series or in parallel in certain geometries according to what is required from the electrical circuit and the performance that we would like to obtain from the electrical circuit. So as an introductory section to this field, before discussing the electrical circuits, we would like to encounter the effect of connecting resistances or resistors in series or resistors in parallel. And first of all, we consider resistors in series, and in this case, if we have n resistors connected in series, connecting in series means that the same current flows in all the resistors. So the first resistor, the first terminal of the first resistor is connected with a point at voltage V, and then the second terminal is connected with the first terminal of the second resistor, and so on, until the last resistor R sub n, the end of it, the second terminal of it, is connected with some reference point at reference potential. We assume that it's the ground. V is equal to 0. Of course, this is not required. We can always assume that the first point is at voltage V1 and the last point is at voltage V2. In this case, V is equal to V1 minus V2. It's simply the voltage difference. V is the voltage difference between the the beginning of the series of resistors and the end of the series of the resistors. The current is constant across all the resistors, but the voltage is divided across the resistors. So the total voltage drop from the initial point to the final point by the end of Rn is simply the voltage across the first resistor, V1 plus V2 across the second resistor, and so on. So the total voltage is simply the summation of V sub k from k equals 1 to n. K is just an index that's running from the first resistor to the last resistor. That's V. And substituting for the value of V, the total V is simply the total I current flowing through the equivalent resistance. So if we look at these resistors R1, R2, R3 connected in this way, if we imagine that they are equivalent to a single resistance with resistance R, then V, which is IR, is equal to the summation of Vk running over all the individual resistances. And Vk is simply the current through the resistor, I, which is the same as the current flowing in each resistor is the same, constant, times the resistor itself, Rk. So I times R is equal to the summation of I times Rk running over all the resistors. And now we can eliminate I from both sides, and we get the equivalent resistance for a set of resistors connected in series is simply equals to the summation of the individual resistances. So the equivalent resistance for a number of resistors connected in series is simply R1 plus R2 plus R3 and so on. So this is for connection in series. And now we consider a set of resistors connected in parallel. In this case, if the resistors are connected in parallel, that means the two ends of each resistor are connected to the same 2 points with potential difference V between them. So one end is connected with the point at potential V, and the second end of the resistor is connected to the second point, which is at reference potential 0. So essentially, and all of them are done the same way, connected the same way. So essentially, the potential drop across each resistor is the same. But the current, this time, the total current emerging from the point at V will be divided into the individual currents R1 plus R2 plus R3 passing through the different resistors. That's the total current, but the voltage is the same. So in that way, in order to calculate the equivalent resistance for this set, we assume that this set is equivalent to a single resistance with resistance R, equivalent resistance, and noticing that the voltage drop across each resistance is the same, the current splits at each junction, and as we mentioned, the total current going from the first point at V and ending in the second point at potential 0 is equal to the sum of the individual currents in the branches. I is equal to summation over K of IK. And now substituting for I using Ohm's law, the total current I is simply the potential difference between the 2 points where the resistors are connected, V, divided by the total or the equivalent resistance, the net resistance. So I is equal to V over R is equal to summation over K from K equals 1 to N of IK. IK is by definition the voltage drop across the resistor, which is V, divided by the resistance of that resistor, RK. So now we have received this formula from which we can calculate the equivalent resistance. V is the same in both sides of the equation. If we eliminate V, we reach a result for calculating the equivalent resistance of resistors connected in parallel. And this formula states that 1 over the equivalent resistance, R, 1 over R is equal to the summation of 1 over RK from K equals 1 to N. N is the number of resistors connected in series. Thus, what do we have is if we have a set of resistors connected in series, the equivalent resistance is calculated from 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on. And we add up, and that way we calculate the equivalent resistance R by inverting the result by the end. And now, suppose that we have a circuit where it has both types of resistor connected in series and in parallel. What do we do? In this case, we apply the rule for determining the parallel resistors, the equivalent resistance for the parallel resistors, and we apply the rule for the calculation of the equivalent resistance for the series resistances. So we apply both rules where it applies in the circuit, and if the resistors are connected in a simple manner, that way using these two rules we can determine the equivalent resistance of the whole circuit. And now we will move to a new topic, which is Joule effect or Joule heating. The current, when it passes through a wire, a conductor, it heats up that wire, like what happens in the light bulb, for example. In the light bulb, when current passes through the light bulb, it produces a lot of heat. It becomes hot. And that is the so-called Joule heating or Joule effect. This is heat energy produced by the passage of current through a conductor. And now we will be encountering this problem. The electric field in a conductor, as a consequence of the potential difference across that conductor, the electric field does work to drive the charges through the potential difference between 2 points in the conductor. So it does the electric field does work, and that work that is done on the charges as they move across the potential difference in the conductor is simply if the charges are assumed, if we take a small amount, an element of charge dq, and we assume that this charge dq moves an element of length of the conductor dl, then the work done during this motion of this little charge element dq is simply the force exerted on this charge element by the applied electric field, of course, times dot product with the displacement of this charge element dl vector. And that by using the definition of the force is simply the charge times the electric field, and the charge is this element of charge dq times E that gives the force dot dl, the path traversed by dq. That will give us the amount of work, or the elemental work that is done on this element of charge as it moves a displacement dl along the conductor. Now, as an example, first of all, we consider a resistor with current I. In order to calculate the work done, we consider a resistor with current I, a uniform resistor with current I. The work done in this case is dq, which is I dt, that during a time interval dt, the charge carried across any cross-sectional area of that resistor is simply I dt. So this is dq times E, the electric field, dot dl. That gives the work, and this is simply equal to I times dt, and E dot dl is simply the voltage difference. Between the first point and the second point where the charge is drifted or carried along the conductor. So dV is the potential difference across this element of path across which dq moves. And then the power dissipated due to this motion is simply the work done divided by the time, and this work is associated with the length element dl, of course, so it's dp, which is dw over dt, and this dp associated with the element dl across which the voltage is dv is equal to I times dv, where dv is the potential difference along this element of path dl, as we have mentioned before. So this is the power dissipated as the charge element moves a length dl across the conductor. And the total power dissipated in the resistor can be calculated by simply integrating. This is dp, so equals I dv. So the total power P is by integrating I dv, and the integration of I dv is equal to simply I times V. So the total power dissipated in the resistance R is simply the current passing through the resistance times the potential drop across the resistance. That is the total power dissipated in the resistance. And alternatively, we have Ohm's law, which relates current, voltage, and resistance, and we can use that in order to obtain alternative forms of the power dissipated, and this is either P is equal to R I squared or V squared over R, and these are obtained by using Ohm's law in the macroscopic form, of course. And secondly, we consider an infinitesimal volume, the second approach an infinitesimal volume d tau where the current flows, d tau of the conductor. And then we consider that the number density of charges in this volume element is simply n, and each charge is q. So n times q times the volume itself, that is equal to the charge dq. And then the work done, we substitute this in the formula of the work, is equal to dq, which is nq dt, times E dot dl, which is d tau actually, nq d tau, that is the volume element, times E dot dl, which is equal to d tau, the volume element, times the electric field E dot the quantity nq dl. But dl is the path traversed by the charges, which is simply the drift velocity v times dt, times the time taken by the motion. V dt is the length traveled by the charges. So with these in mind, the work done per second, which is the power on the charges in the volume element, can be obtained by dividing by dt, by the time, and dividing by dt we obtain dp is equal to d tau, that's the volume, times the electric field dot n, the number density, q, the charge of each particle, times v, the drift velocity. And that is simply d tau, the volume element, times the electric field dot j, the current density across that element of volume. And this gives a local equation, which is the power dissipated per unit volume at a given point in the conductor, dp by d tau, power per unit volume, is equal to E dot j. And using the microscopic form of Ohm's law, this is equal to sigma E squared or j squared over sigma. This is by using the microscopic form of Ohm's law. And this result is consistent with the previous result. We have calculated the power in two different ways, but they should give the same result. And how are they consistent? Let's start from the result of the first method of calculation. P is equal to I squared R, which is equal to, substitute for I by j, j squared, A is the cross-sectional area, times L divided by sigma times A, and this is substituting for R, or the resistance, which is equal to j squared over sigma times A times L. A times L is the volume, of course, of the conductor. So P over AL, which is the power per unit volume, is equal to j squared over sigma, which is exactly the same result that is obtained before. This power appears as a thermal energy in the resistor, leading to the effect called Joule heating. And this effect is the basis of all electrical heating applications and appliances. And at this point, I finish my lecture, and I thank you for your attention.